Good afternoon, guys. Welcome to the class.
The lab we learn how to determine alkalinity of water. So we know by now that alkalinity is basically what? Alkalinity is
The acid neutralization capacity, right? Basically, this is the opposite of acid. Opposite of acid. Acid neutralization capacity. Alkalinity can be caused by a multitude of species, but in the majority of the cases, who causes alkalinity? The alkalinity of natural water is due primarily, most of the cases, primarily means most of the cases, to the salts of weak acid. The salts of weak acid. For example, bicarbonic acid is a weak acid, H2CO3. So it gives you bicarbonate ion, which gives you. So this is if it's present in water that can consume hydrogen ion. Okay, this has the capacity to consume hydrogen ion. Then again, HCO3 can give carbonate ion and hydrogen ion. So this has the capacity to capture hydrogen ion, right? And we can also get alkalinity from hydroxyl ion. Okay, basically, if the pH is higher, we get hydroxyl ion and hydrogen ion. So these are the species. These are the species which causes alkalinity in water. Which causes alkalinity in water. Clear?
Yes, sir.
In groundwater, for example, this is a soil. You have the groundwater here. In soil, you have carbon dioxide dissolved in water, right? And also you have calcium carbonate. It's like a rock, water, right? Calcium carbonate. So the water is in contact with calcium carbonate and this carbon dioxide. So this carbon dioxide and calcium carbonate in water, they produces calcium ion and bicarbonate ion. Calcium bicarbonate basically. This is basically calcium bi basically calcium bicarbonate. Calcium ion and bicarbonate ion. Calcium ion and bicarbonate ion. So this is actually alkalinity. Are you following me?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Now we know that with the variation of pH, there might be different types of alkalinity. For example, when we have a pH at less than 4, then mainly H2CO3 is undissociated. So less than 4.5 here is undissociated. That means it does not dissociate at pH less than 4.5. It only dissociates when pH is greater than 5. Then it dissociates and gives bicarbonate ion and hydrogen ion. When your pH is, and you can see from here at this 4.5, right? Here is 4.5. You can see at 4.5, this curve is for whom? H2CO3. This curve this line, this curve is for whom? For whom? Tell me. Bicarbonate. And this line for whom? Carbonate.
Carbonate.
This is for bicarbonate, carbonate, and this one is for H2CO3. At 4.5, as you can see here, it should be here. As you can see here, all are H2CO3, and these are in very negligible amount. For example, HCO3 is very negligible amount, and H plus is also very negligible amount. Why negligible? Because this is log scale, guys. This is log scale. Okay, this is 10 to the power minus 2, and this is what? 10 to the power minus 4. Basically, log scale. That's why log 10 to the power minus 4 is what? Minus 4. Log 10 to the power minus 3 is what? Minus 2, right? So basically, you know that 10 to the minus 2, 10 to the minus 4. How much? 100 times. Am I right? Hello?
Yes, sir.
Yes, sir.
So this is very high concentration relative to the others. And you can see at pH 6.3, carbonic acid is equal to bicarbonate. Look, let's look at here. At pH 6.3, here maybe, these two curves merge. That means the concentration, I'm sorry, not this one. 6.3 is here, right? Around, this is 7. 6.3 is here. It should be here. So at this point, as you can see, at this point, H2CO3 and H2O3 mix together. That means they have similar concentration. Clear? They have
Yes, sir.
similar concentration. Equals to this. Right. So the objective of this graph is to show you that at different pH, there are different species. Okay, and you can see that as pH decreases from 10 to 10 to 2, hydrogen ion concentration increases. As you know that at lower pH, that means acidic, that means hydrogen ion will be higher. As
Yes, sir.
pH increases here, who will increase? Hydroxyl ion will increase. And you can see that yes, hydrogen ion is increasing. And with decreasing pH, H plus is increasing here. Or you can say with increasing pH, hydrogen ion is decreasing and OH is increasing. With increasing pH, hydrogen ion is decreasing and OH is increasing. Am I right?
Yes,
Yes,
sir.
sir.
Environmental significance of what? Alkalinity. Why you are concerned about alkalinity? As mentioned earlier, alkalinity is a measure of buffer capacity, and in this sense is used to a great extent in wastewater treatment practice. If your water has high alkalinity, then you will need a lot of acid to reduce the pH. Am I right?
Yes, sir.
Yes, sir.
If you have low alkalinity, then even a slight change of acid will make a huge difference in pH. All right.
Yes, sir.
If high alkalinity is there, it has a buffer capacity. That means it can hinder the pH of the water to change. That means it tries to keep the pH constant. But that's why you need a lot of acid to change the pH. It tries. Okay. As mentioned earlier, okay, fine. So alkalinity is very important in iron removal from water by oxidation precipitation process. Iron removal. This is important. Very important. For example, do you know how do we remove iron? In water, iron is in dissolved form, Fe plus 2. This is dissolved, aqueous. Here, what is the valence here of iron? Yes. What is the valence?
2.
2. Now, if you want to remove the iron, what you need to do? You need to oxidize this and make it ferric. From ferrous, you need to convert it to ferric. One example is ferric oxide, Fe2O3. And this is solid. This is solid. So whenever you convert oxidized iron with oxygen, it will become ferric oxide and it will no more be in dissolved form. It is, since it is solid, it will precipitate. It will precipitate. This iron will precipitate. This iron first will be transferred to ferric and then this ferric will precipitate. That means that's how you can remove the iron from water. Now, how do you add oxygen? You can add air. Air has oxygen, right? Right?
Yes, sir.
Yes, sir.
If you can add air into the water, that can remove iron. But for this reaction, for this oxidation to be effective, the alkalinity of this water has to be greater than 130 milligram per liter at least, or 150 milligram per liter. If your alkalinity is less than 130 milligram per liter, then it is very difficult to do this. That means if alkalinity is low, this oxidation will not take place easily. That means your removal will be smaller. Or you want to remove the iron, right? So you have to keep alkalinity greater than 130 milligram per liter. Is it clear?
जी सर.
So that's why they're telling alkalinity is very important in iron removal from water by oxidation precipitation process. So first of all, it gets oxidated and then it precipitates. So it's called oxidation precipitation process. It has been found that the rate of oxidation of dissolved ferrous iron into insoluble ferric iron is very slow for low alkaline water. As I told you, less than 130. If this is less than 130, then it's a problem. Clear?
Yes, sir.
That's one thing. And regarding the health significance, alkalinity does not have much health significance. It's not that much harmful for our health. Clear?
Yes, sir.
Okay. Now, how to calculate alkalinity? Very easy. If you here, right? For example, you have water here, whose alkalinity you want to measure, right? Whose alkalinity you want to measure. Now, what we do in alkalinity is Alkalinity is basically what? The opposite of acid. So we measure it by applying acid. For example, here in this sample, in this sample, if you add phenolphthalein, if you add phenolphthalein, P indicator, and it turns out as pink after addition of phenolphthalein, if you see that this becomes pink, that tells you that your pH is greater than 8.3. Am I right?
Yes,
Yes,
sir.
sir.
Either 8.3 or greater than 8.3. That means you have alkalinity. Which alkalinity? You have P alkalinity in this. If your pH is in between 4.5 to 8.3, I mean this range, you have M alkalinity. This M alkalinity. Now, if your after addition of phenolphthalein indicator, you saw that your um, water turned into pink. That means you are greater than 8.3. Then you add from the burette, you add sulfuric acid or other type of acid you can use. Uh, we may use sulfuric acid here. 0.02 normal. What's the concentration? 0.02 normal. So H2SO4 0.02 normal concentration of sulfuric acid. So you add acid. Now pH will be, for example, your pH was greater than 8.3, right? For example, 10. Your pH was 10. Now after addition of H2SO4, what would be your pH? Less than or greater than 10?
Less than,
Yes,
sir.
sir.
Because you are adding acid. Okay, so it is decreasing, decreasing, decreasing. At 8.3, this pink color will be colorless, alright?
Yes, sir. Vanished.
Colorless. So you measure how much sulfuric acid you have added. How much sulfuric acid you have added. Volume 1, for example. Now, you add, when you see colorless, you stop adding sulfuric acid. Now you add methyl orange indicator. Now you add methyl orange indicator. And you'll see that it may be colorless. Okay, fine. Now you again start adding H2SO4. So at a time it will be yellow color, and you'll see at a point the color will turn from yellow to orange, and that's your end point, 4.5. Remember, that's 4.5, and beyond that point, I mean below that point, there is no alkalinity. So you are here now. By adding acid, you are now here, because your color has turned from yellow to orange. So you're here. Is it clear? Is it clear?
Yes, sir.
Yes, sir.
So you measure the second volume, V2. So the volume of the sulfuric acid corresponding to the first step, that is basically the P alkalinity, because you stopped at 8.3, and from 8.3 and beyond, that is P alkalinity. And the volume of the sulfuric acid that you added in the second stage, I would rather say, that is basically the M alkalinity. Clear?
Yes,
Yes,
sir.
sir.
If you add this V1 plus V2 corresponding to the volume of H2SO4, that is basically the total alkalinity. Clear?
Yes, sir.
Now, so now here is the catch. At the very beginning, we added what? Phenolphthalein, right? And it turned into pink. But instead of pink color, if you had found that after addition of phenolphthalein it was colorless, that means your pH is less than 8.3. Am I right?
Yes, sir.
So you directly add methyl orange. You don't need to add any acid anymore. You directly add methyl orange and you measure, and then you add H2SO4 and measure. Clear? That means you will only get M alkaline. This means your sample did not have P alkaline. Okay?
Okay, sir.
So let's see what they're telling. Take 100 ml of the sample, fine, and the same amount of distilled water into the beaker to compare the color. That's it. The distilled water is to compare the color. Measure pH of the same sample with the pH meter. So you need to measure the pH. Add 3 drops of phenolphthalein indicator to each. So phenolphthalein indicator. If the sample becomes pink, go to step 4, and otherwise go to step 5. That means if it's colorless, then you do not need to have this fourth step. You don't need to have this fourth step. You can directly go to fifth step and add methyl orange. Clear?
Yes, sir.
Okay. Now,
Sir,
yes.
sir, if there is no phenolphthalein alkalinity, then what will be the total alkalinity? Just M alkalinity, right?
Yeah. Total alkalinity
Oh,
is the
oh, okay, sir.
I mean, total alkalinity equals to M alkalinity plus P alkalinity. So, M alkalinity, for example, 10, or P alkalinity is 0. So, 10 plus 0 equals to 10.
Okay, sir.
So, phenolphthalein alkalinity, first, for example, you have both 4 and 5, pink color. Initially, it was pink color. So, phenolphthalein alkalinity will be multiplied factor and milliliter of 0.02 normal H2SO4 used. That means V1. V1. This is V1. And total alkalinity is the amount of V1 plus V2. This is V1 plus V2. So, this is V1 plus V2. Clear? Now, what is multiplying factor? Multiplying factor easily can be calculated equals to normality of H2SO4. Normality of H2SO4. What is the normality of H2SO4? Tell me. 0 normal, right? That's acid you have used. 0 normal H2SO4. 0 normal H2SO4. You have added. So
Okay, sir.
equivalent weight of calcium carbonate. Again, equivalent weight of calcium carbonate equals to what? Molecular weight of calcium carbonate divided by valency, am I right? So molecular weight of calcium carbonate is calcium 40 plus carbon 12 plus oxygen 16 into 3, am I right? Huh?
Yes, sir.
Yes, sir.
So from here, 48, 12, 60 and 40 is 100 by 2. This is actually 50. So this is 50 into 1000. So you have a milliliter of sample taken. How much? What's the amount of sample you took? 100 ml. 600. That's it. Okay, so it's done. Is it clear?
Yes,
So
sir.
now you calculated phenolphthalein alkalinity, total alkalinity. Fine. Now this total alkalinity is measured as milligram per liter as calcium carbonate. That's fine. What I wanted to say here is that the total alkalinity, this total alkalinity is a summation of, remember, bicarbonate ion plus carbonate ion plus hydroxyl ion. That means total alkalinity is bicarbonate alkalinity plus carbonate alkalinity plus hydroxyl alkalinity. Am I right?
Yes, sir.
Yes, sir.
Sometimes you may want to know or measure them individually. So now we will learn, if we know the total alkalinity, then how we can determine this bicarbonate alkalinity, carbonate alkalinity, and hydrogen alkalinity. First of all, if this is the water molecule, it dissociates to give you hydrogen ion and hydroxyl ion. And at 25 degrees Celsius, you have a constant Kw, which is the concentration of hydrogen ion and multiplied by concentration of hydroxyl ion, which is 10 to the power minus 14. Now, if you have acid and acid H2CO3, of course, acid give you hydrogen ion and bicarbonate ion, and you can again have a constant, which is concentration of this here, concentration of bicarbonate ion here, and concentration of H2CO3 here. At 25 degrees Celsius, this is 6.3 for bicarbonic acid H2CO3. Again, this HCO3 minus, this one, dissociates to give you hydrogen ion and carbonate ion. And again, you can have a constant. This is hydrogen ion concentration, carbonate ion concentration, and bicarbonate ion concentration. This one. This is 10.3 at 25 degrees Celsius. This is called acid ionization constant. This was water ionization constant, and this is acid dissociation constant. Acid dissociation constant. Which one? AA. Ka. Ka1 or Ka2. Acid dissociation constant. If the acid is stronger, then Ka will be also higher. Ka value higher means the acid is stronger, because the acid, if the acid is stronger, then you will get more and more hydroxyl ion, and if there is more and more hydroxyl ion, then your acid dissociation constant will be higher, because H plus is on the numerator. Is it clear?
Yes, sir.
Okay. Now, if you want to know the carbonate alkalinity, that means this one, carbonate alkalinity, then the formula is 50,000 into alkalinity divided by 50,000 hydrogen ion concentration, Kw divided by H plus this. That means, let's do this. 50,000, alkalinity. What is alkalinity? You already determined this. Total alkalinity, this one. Okay? Milligram per liter as calcium carbonate. This is the alkalinity you just measured. Okay?
Okay, sir.
You want me to correspond to this. Okay? This B correspond to this. Okay, so you know this. H plus. What is H plus? Did you see you measured pH? Huh? Right? Huh? You measured pH, right?
Yes, sir.
Yes, sir.
You know the pH. For example, pH is
We don't know, maybe 8.5 or maybe 8.6. And what would be pH? pH is what? Minus negative logarithm of hydroxyl ion. So from here you can write pH is basically this minus negative logarithm of hydrogen and concentration. So you can write this minus 8.6. So you can write hydrogen ion concentration equals to 10 to the power minus 8.6. Am I right?
Yes, sir.
So hydrogen ion concentration you know where? Here. So you put the value here. Kw you know at 25 degrees Celsius you have 10 to the minus 14 Kw. So you know this value. H plus again you know H plus. I just determined. K2, what is K2 at 25 degrees Celsius for bicarbonic acid? What is K2? 10 to the power minus 10.3. So 10 to the power minus 10.3, you know this. Clear? So all values are known, so you can calculate carbonate alkalinity. Is it clear?
Yes, sir.
Yes, sir.
Clearly, if you want to know bicarbonate alkalinity, this one, the formula is this. Again, you know everything, so you just put the value, you can calculate. To calculate the hydroxyl alkalinity, this is the formula. 50,000 into 10 to the power pH minus KW, pKW. pH you know 8.6, right? Or whatever you get. And pKW, you know this. pKW is what? If you know KW, then what is the pKW? What is pKW? KW 10 to the minus 40. KW equals to 10 to the power minus 40. So pKW is what, guys? Minus negative logarithm of KW, am I right? Huh?
Yes, sir.
Yes, sir.
So minus negative logarithm of 10 to the minus 14. So it becomes minus, minus log of 10 to the minus 14 is minus 14. So it becomes 14. So pKW is actually 14. So you put the value here. Here. There. And the unit, remember the alkalinity unit, we represent it as what? Milligram per liter as calcium carbonate. Equivalent to calcium carbonate. So all the unit is in milligram per liter calcium carbonate. Clear? Is it
Yes,
clear?
sir.
Now, sometimes actual concentration of carbonate and bicarbonate ions may be desired. I mean, here you have expressed bicarbonate alkalinity in terms of calcium carbonate. In terms of calcium carbonate. But if you want to know the bicarbonate alkalinity in terms of bicarbonate, then what do you need to do? You just need to, uh, in case of carbonate, you need to multiply this value, whatever you get from here, with 0.6, and you need to, for bicarbonate, you need to multiply this value, whatever you get from here, with 1.22. That's it. Clear? You're just converting the unit, nothing else. You have already determined this. Now you are just converting the unit from kg to milligram, milligram to kg, something like that. Is it clear?
Yes, sir.
Yes, sir.
Again, you can convert it to molar concentration also. In that case, this milligram per liter carbonate, this one, has to be divided by 60,000. And for bicarbonate, you need to divide this value by 61,000. That's it. Simple. Clear? Is it clear, guys?
Yes, sir.
Yes, sir.
So that's it. How did this 1.22 came from? Where did this 1.22 came from? Hmm? You're converting into bicarbonate, right? So bicarbonate equivalent weight কত? 1 plus 12, right? 13, 48. So equivalent weight হচ্ছে 1 plus, let's do it, bicarbonate, HCO3 minus 1 plus 12 plus 48. Am I right? 61,
Yes,
right?
sir.
Okay. What is the valency? 1. So 61 by 1, 61. So 61. And converting from calcium carbonate. Converting from calcium carbonate. So calcium carbonate equivalent weight কত? বের করতে একটু আগে। 50, right? 50, right? Right?
Yes, sir.
So it divided by 50. কত আসে বলো তো? কত আসে?
1.22.
1.22. ঠিক আছে? 1.6 কোথা থেকে আসলো? সিমিলার, এটা কার্বনের। আগে এটা বাইকার্বনেট ছিল, এটা হয়ে যাবে কি? কার্বন। কার্বনেট কত? 12 প্লাস 3 ছিল 48, তাহলে 60, তাই তো? হুম?
Yes, sir.
60, তাহলে 60, আর এটা ভ্যালেন্সি কত? 2 না? কত আসে? 30। তাহলে 61 যায় কি হবে? 30। 30 বাই 50 কত আসে বলো?
0.6.
0.6, তাহলে 0.6। আমি যে দেখালাম কোথা থেকে আসছে এটা। ক্লিয়ার?
Yes, sir.
Fine. Any questions? Any questions?
No, sir.
Okay then, thank you very much. Have a good one and stay safe.